Boker Tov and good morning to all. Today I want to try to understand a little bit further what are norms by visualizing them using something called the unit balls. In general, this material is not necessary for the rest of this course. I still think that this is quite interesting, so I'm adding it nonetheless. Okay, so let's start. Let's start with a reminder. We have the norms. So the norm is a function from the vector space into R. It should be non-negative, right? The norm of V is larger than 0, and it is 0 if and only if the vector is 0. It should be absolute homogeneous. The norm of alpha V is the absolute value of alpha times the norm of V. And finally, it should satisfy the triangle inequality, right? The norm of V plus W is at most the norm of V plus the norm of W. And now that we have the norm, we can define the unit ball. So again, we start with any norm on the vector space V. It doesn't have to come from an inner product space. And we define the unit ball as all the vectors with norm at most 1. We can also talk about the unit sphere, and these are all the vectors with norm exactly 1. So again, you start with the norm, and then you define the unit ball and the unit sphere. So let's see an example. And I want to take the Euclidean plane. So our norm is the square root of x squared plus y squared. And if I ask you what is the unit ball, then we get exactly this. Right? This is the unit circle. Now, in general, we call this always the unit balls because we want just one word for everything. But because we are on the Euclidean plane, we can also talk about the unit circle. Okay, so the curve itself, the yellow curve itself, is a unit sphere. What we have inside is the unit ball. And I will soon talk about other norms, and we will try to understand how their unit balls look like. But before I do that, I just want to talk a little bit in general about these sets of unit balls and try to understand what sort of properties do they have. For example, right now we started with a norm and we found a unit ball. I'm also claiming that we can go the other way around. So if you give me the unit ball, I can actually find the norm itself. So let's see how. Let's say that you give me this unit ball, that whatever I see on the screen, and you give me some vector w, and I want to find the norm of w. Then what I'm going to do is I'm going to start and shrink this vector and stop exactly when I hit the unit sphere. And because I can find the scalars that get me to the unit sphere, and the guess is that this scalar should be 1 over the norm of w, then I can find norm of w. Now take it as an exercise and show that all of this is true. But again, if I have the unit ball, then I can also go back and find the norm itself. Okay, so this is the example. Let's talk a little bit more about the properties of the unit ball. And I want to ask, how does a general unit ball look like? Okay, so for example, can this set be a unit ball of some sort of norm? So I claim that this cannot be, and the reason is that if I look at a zero vector, then the zero vector has zero norm, and then by definition it has to be inside the unit ball. And this set does not contain the unit vector, so it is not a unit ball of any norm. Okay? So this is really, really simple. Any unit ball must contain the zero norm, the origin. Fine. So let's move it a little bit. Now it contains the origin. Can this set be a unit ball? Right? Take any norm that you want. Can you find a norm that this is the unit ball of this norm? So I claim that again this is not true, because if I look at this vector v, which is inside the unit ball, and I look at its opposite, I look at minus v, then we know that the norm of v and the norm of minus v is the same norm. And because one is in the unit ball, so it is at most 1, then the other should be at most 1 as well. Or in other words, one vector is in the unit ball if and only if the minus of this vector is also in the unit ball. And since this is not the case here, this set is not a unit ball. Now this property that whenever you have one vector, you have also its minus, this is exactly saying that the set is symmetric. Great. So now we have these two very nice and geometric properties. The unit ball must contain the origin, and also it should be symmetric. And this more or less corresponds to the non-negative and absolute homogeneous properties of the norm. And we need to have a third property which somehow corresponds to the triangle inequality. So let's try to understand it. So this is a new set. It contains the origin, it is symmetric, but it's not going to be a unit ball. So let's try to understand why. If you give me any 2 points, and you connect these 2 points by a segment, then my claim is that if you started with 2 points inside the unit ball, then this entire segment must be also inside the unit ball. Okay, I claim that we have this property. So let's prove this claim, or at least let's prove this claim for 1 point, the middle of this segment. So I want to show that if I start with 2 points in the unit ball, so the norm of V and the norm of W is at most 1, then I want to show that the norm of V plus the norm of W divided by 2 is also at most 1, right? It is also should be inside the unit ball. Okay, so let's try to understand it. The norm of V plus W divided by 2 using the triangle inequality is at most the norm of V divided by 2 plus the norm of W divided by 2. And now we can take the 1/2 and take it outside of the norm to get half the norm of V plus half the norm of W. And because the norm of V and the norm of W are at most 1, then this entire summation is also at most 1. So again, we have this very nice geometric property. If you have any 2 points, then the segment between them must be inside the unit ball. And this property is called the convexity of the set. So for example, if I start with this star set and I want to fix it in order to be convex, then I get this nice square, which is a little bit rotated. Okay, so now we have this property, so let me just write it down. So the answer is if you have a general unit ball, then first it should be non-empty, or it contains the origin. It should be symmetric. If it contains V, then it contains minus V. It should be convex, so any 2 points that are inside the unit ball, then the entire segment between them is also in the unit ball. And finally, one more property that it should be bounded, right? Because we're talking about vectors with norm at most 1, so we cannot go to infinity. Okay, so now we have these 4 very nice and geometric properties, and at least for me, it is much easier to look at a set and see that it satisfies this condition, at least in lower dimensions, than actually look at some function and check that it satisfies the conditions of a norm. And moreover, if you really wanted to, you can actually prove that any set which satisfies this 4 condition is unit ball of some norm. Okay, so this is more or less a parallel definition for this norm. Okay, so I want to finish with a little bit more visualization and try to really see this unit ball of norms. And I want to talk about 2 family of examples. So the first one is the LP norms. So recall that the LP norm of a vector V, we take the vectors in absolute value, we raise to the power of P, we sum up the coordinates and then take 1 over P. And one thing interesting about looking at the unit ball or the unit sphere is that if you want just the unit sphere, if you want to equate it to 1, then the norm is 1 exactly when the sum of the Vi to the power of P is 1. Right, so we can remove the 1 over P, which is a little bit more complicated. Okay, so these are the LP norms that I want to talk about. The second family are induced norms. So let me remind you, we have seen that if we have 2 vector spaces and we have some map from one vector space to the other, and we have an inner product in the second vector space, then we can pull back this inner product to the first vector space. So again, we wanted to understand one vector space through another, then we can pull back this inner product. And when these 2 vector spaces are just standard vector spaces, they are R to the N and R to the M, and the map between them is multiplication by a matrix A, then we saw that the definition of the inner product is just W transpose A transpose A V. Right? We have this A transpose A as the cost of this transformation. Okay, so I want to look at these norms as well. And what's interesting about them is that if I ask when is this new norm 1, so when is the inner product of V by itself is 1, but under this new inner product, then this is the same as asking when is AV transpose times AV is 1, which is the same as taking the standard Euclidean norm of AV and ask when this is 1. Now, if you think about it for a second, taking the norm, the standard norm of AV is just sum of squares. So what I see on the right-hand side is just some simple functions in the coordinate of A and the coordinate of V. So I can just tell the computer, plot me the sphere of this function. Okay, so this is what I'm going to do. I'm going to look at the LP norms. I'm going to look at these induced norms, give it to the computer and see what happens. Okay, so let's see. Great. So now I'm using GeoGebra to plot the unit sphere of these norms, and there is a link below if you want to check it as well. So this is the unit sphere in the L2 norm, in the standard Euclidean norm, and I'm soon going to drop it to 1, and in the meanwhile try to think what is going to happen. So I'm dropping it from p equals 2 to p equals 1. So as I'm dropping it, getting smaller and smaller until I get a diamond or a square rotated. Now you can check it out that the L1 norm is just absolute value of x plus absolute value of y equals 1. So if I'm in the positive quadrant, so x and y's are positives, then this is just x plus y equals 1. So this is a line, and this is going to be this line. And the same happens in the other quadrant, and this is why I get this diamond. And I can also decrease it further, for example, p equals half, and you can see that this set is no longer convex. So this is why when you talk about the LP norms, you start with p equals 1 and you go to infinity. Okay, so let's increase it back again to p equals 1, and then we increase it back to p equals 2 and get the actual circle. And of course, if I increase it further, then it looks something like that. And you can see that as p grows larger and larger, we get closer and closer to being a square. Right, so in a sense, we start with a square in p equals 1, and we end with a square with p equals infinity, but we just rotate it a little bit and shrinking or stretching it a little bit. Okay, so these are the LP norms in 2 dimensions. I also want to show you this in 3 dimensions, so I need a different program for that. And this is it. So these are the unit balls for the LP norms in 3 dimensions, where p runs from 1 to 3. So for example, let me try and stop at p equals 1. So this is p equals 1. So now you get an actual diamond with 8 faces, and each face is a triangle. And if I let it increase up to p equals 2, so I think this is more or less p equals 2, we get a sphere or an actual ball. And if I increase it again up to p equals 3, and when I go to larger and larger p, you get closer and closer to actual cubes. So notice that unlike the 2-dimensional case, where L1 and L infinity looks the same, right? Both of them look like a square. Now L1 is an 8 faces diamond, and L infinity is going to be a 6 faces cube. Okay, so they are actually different. So something special happened in 2 dimensions, in 3 dimensions and above, you get something different. Okay, so again, this is something that I can actually see with my eyes, and I don't need to run the actual computation to understand it. Okay, now before I go to the second family, I just want to go a little bit into the code. And this is the actual code. And again, if you want, there is a link in the description below to this code and to this program, and you can check it out. I need to warn you in general, this is not a specialized code for this animation. This is actually a more generic code for something called ray marching. And at least in my opinion, ray marching is one of the more interesting algorithm out there, because on the one hand, it is quite simple, and on the other hand, you can do very amazing animation with it. You should really look it up. And one of the important part in this ray marching algorithm is that you need to define a function which tells you the distance from a point to some object. And we're speaking about norms. This is exactly what we do. So if you want, this is the function, the distance to the scene, and this is the function which actually computes the LP norm. So if you want, you can actually go inside the code, and I wrote it here in more detail, and you can play around with it. So if you have the LP norm, you see what we saw before. You could take a norm that maybe defines a cube, or maybe defines a cylinder, or maybe defines other objects. And actually, the fact that you start with a norm makes this function runs better. I think that if you do stuff which, for example, are not convex, it is actually harder to do. Okay, so these were the LP norms. I want to go back to the induced norms. So we're back in GeoGebra, and I want to look at this function. We take some sort of 2x2 matrix, should be invertible, and we take the standard Euclidean norm, and we ask what are the x and y such that the matrix times xy, the norm is exactly 1. That's something that a computer can actually write down. Okay, so I'm going to play around with the coefficients of the matrix. So let's start with the A coefficient. and see what happens to the unit ball. So if I increase it, you can see that the unit ball just changes to unit ellipse, or not unit anymore, just ellipse. So a bigger A means the ellipse looks like that, and a smaller A looks like that. And as I go to 0, which is non-invertible, so this is not actually a unit ball, we just get 2 lines. And if we go further more, we get back to a sphere. Okay, so this is just one thing. We can also do it with this, so this is this coordinate. And we get something similar, again ellipses, but they stretch and shrink in different direction. So again, we can take a circle and change it into an ellipse, and whether we change the A or the D changes whether we stretch it along the x-axis or the y-axis. If we change, for example, the B, so we change it from 0 to 1, so again we get an ellipse, but it was not stretching or shrinking, right? It is some sort of moving parallel. This is called shearing. So again, we get an ellipse, but something which looks like that. And again, I can start to play around. So if I change C, and now if I change D, it looks like that. Okay, so all of them gives me ellipses. So again, this is something interesting. No matter which matrix you take, you always get ellipses. Now let me give you a little bit of spoilers. Many times that you try to do algorithms in machine learning and you have some sample inside your vector space, you will get some sort of such ellipse. And you would want to ask, okay, what is this axis and what is this axis? And what are the lengths? Because these are going to be important, because you say most of the information is spread around this axis, and then the second most is around this axis. And if you're in higher dimensions, you can talk about more and more axes. And this is a very important question to ask. And the fact that it looks like an ellipse here is not a coincidence, because in general, most of the time that you see this type of ellipses, they come from this type of computation. Okay, so this is a little bit of spoiler of what happens in the future. Okay, so at this point, we know what are inner products, we know what are norms, we know how they behave, we know a little bit about visualizations, and this is in a sense the beginning point of the course. And next time we return to the standard material, and we're going to talk about perpendicularity and start to actually prove new results and very interesting results, which will lead us to all sorts of interesting applications. Okay, I will see you next time.